This is starting as a passion project. I love chemistry, and clearly if you're watching these videos, you have an interest in it too. Now, the book that I'll be going off of and reviewing is the Chemistry 6th edition, Zumwahl and Zumwahl. So the cover looks like this is what I will be basing most of the lessons off of. As you can see, I decided to start Chapter 2.8. Chapter 2, Section 8. And the reasoning behind that in Chapter 1 mostly just covers preliminary knowledge to chemistry, scientific methods, and it covers a lot of scientific method, units, measurement, significant figures, which I personally do not use. I find them to be full of it. I prefer accuracy, not significant figures with rounded decibels. Classifications matter, density, temperature, all of that. And a lot of Chapter 2, up until 2.8, is simply an introduction to molecules and ions, the modern view of atomic structures, Dalton's atomic theory, a lot of history behind chemistry. The reason I'm starting at 2.8 in particular, though, is because 2.8 covers the naming molecules. The naming of monoatomics, polyatomics, and covalents. Covalence and covalent bonded molecules. That's going to be the idea behind the video today. So, at the beginning, you may not know what. We have sodium chloride. What does that mean? No, we're not going to do that. Right? What does sodium chloride mean? Or potassium nitrate. Or dihydrogen monoxide. What do those mean? We're going to cover monoatomics, polyatomics, and covalence in this chemistry breakdown. So the question behind why for this episode is I very noisily pull this board out and people flip it. Simply because I have a love for chemistry. I feel like it's one of those subjects that you either hate or love. There isn't really an in-between with it. So you love blowing stuff up or you hate all the equations and stuff that you have to memorize. So this is sort of a series that I'm going to start to help make people interested in it. Okay. So firstly, we're going to start with monoatomic ions. I'm not going to bother writing any of that down. It's really simple. A lot of it's memorized from charges. You have a periodic table. I hope you know what the periodic table is if you're reading chemistry. If not, why are you taking chemistry? I don't mean that. Monoatomics, your lithium, sodium, chlorine, iodine, oxygen. Those are just elements. So if you write out a monoatomic, you simply write out the element. Not necessarily the element, the atomic symbol. Some have a negative charge, some have a positive charge, and some don't have a charge at all. And you don't write it -2, -3. 2 minus, this should be 1 positive, but because there's just one of them, you don't have to write the number 1 in. There's some that just simply don't have a charge, and those are the noble gases. Your helium, your neon, your argon, krypton, xenon. Monoatomics are fairly easy. Binary ionic. Binary ionic compounds are simply one and another. Right out the charges, sodium has a +1, chlorine has a -1. Right, this is table salt, sodium chloride. Why is it called sodium chloride? It's actually decently legible. I wrote that at an angle. Sodium chloride. Why is it called sodium chloride? Well, firstly, your cation, which is the one that positive charge. It could be sodium, it could be ammonium. We'll get to that. It could be hydrogen, whatever it is. Your cation is the one with positive charge. That one always goes first. Your anion, or your one with the negative charge, the chlorine, goes second. So why is it not called sodium chlorine? Typically, that's a good question. You always write the way that you would write it out is that you add the IDE right over here at the end of the chemical name. You remove the last couple of letters, right? Chlorine to chloride, sulfur to sulfide, phosphorus to phosphide, oxygen to oxide. That's real simple. Binary ionics. If you were to write out one that, let's say, and these are your simple monoatomics, by the way. Simple. They do get more complex. So if we were to take FeCl2 to FeCl3, and yes, I am right. That's supposed to be. How could iron have both a plus 2, or a 2 plus, and a 3 plus? Because it's not a simple monatomic. In the case where you're working with a lot of transition metals, I'm going to clean this one up too. A lot of transition metals have more than one charge, more than one electron state. So if you just wrote out iron chloride, the problem, both of these are iron chloride. So how do you think you would write out the chemical formula of iron chloride to demonstrate that it's this one or this one? Parentheses, Roman numerals are your friend. So you write out iron, and iron's first because, again, it's the cation. Let's say we're going after this one. Let's say we want to write iron chlorine. That iron chloride. Open parentheses. Iron 2 chloride. If instead I want to write out this one, it's iron 3 chloride. And the reasoning, look at this. Right. FeCl2. Chlorine's one of the simple monatomics. It always has a -1 charge. If there's 2 of them, and there's only 1 iron, then it's a 2. Then this adds up to a 2 minus. A basic rule in chemistry is that any completed molecule must have a lot of molecules. I shouldn't say all completed ones, but a lot of molecules will have, if it's complete, I guess. If it's not if it doesn't have the ability to have anything attached to it, right? This is a completed molecule. Something like acetate, we'll get to acetate, still needs another electron. So you can still put sodium on it or hydrogen on it. That's not for right now, though. And as you go on through chemistry, you'll learn to look at a molecule and say, I could put something else on that, or it's complete. So this has a 2 minus charge, and the whole molecule is neutral. Then that has to have a 2 plus charge. Or, if this is instead a 3, that makes this a 3, and to make it neutral, I have to have 3 electrons. A lot of metals that you run into will have more than 1 electron state. Iron has 2, copper has 2, cobalt, tin, lead, mercury, they all have 2. Not +2 configurations, although they all do. It's just that they all have 2 or more, right? Iron can be +2 or +2 or +3. Copper could be +1 or +2. Cobalt could be 2 or 3. Tin can be +2 or +4. And lead can be +2, +4. Mercury can be +1 or +2. A lot of information. Again, you'll learn to recognize stuff, and it does help to memorize a lot of the common transition levels that you're working with. You write it out like this because this is not spare, but valence electrons. That's one of the topics that I think is covered in earlier parts of Chapter 2 that it's just preliminary knowledge. Valence electrons are the basis of chemistry itself. That says that this iron has 3 valence electrons, which we know it does. Simple as that. Now, that explains how you name sodium chloride, and that explains how you name iron chloride. The next question, what was that potassium nitride? I did make a mistake because potassium is only one T, not 2. Potassium nitrate. Well, we know potassium nitrate is in the same column as sodium is, and has the same charge. Potassium is K, it's German for cation, which means potassium. For some reason, that's what they wanted with on the periodic table. Same thing with sodium, by the way, it's natrium, Na. So you have a Ki, that's not a Ki. You have a K and a plus. What's nitrate? Nitrite, chlorite, bromate, phosphite, sulfate, oxide. What do these mean? Although that last one doesn't really work. Oxide and oxide, that doesn't make any sense. Well, these are what's called polyatomics. Polyatomics are a bit of a pain because there's a lot of them, but they all follow, a lot of them, for the most part, follow a basic rule. It's going to be a non-metal. It could be nitrogen, fluorine. It could be one of your halogens. It could be a non-metal. Could be mercury. That's not, like I said, that's later down the road. Nitrate. Well, what's the root word? What do you see nitrate? NITR. Nitrogen. I hope that's legible. Nitrogen. So we know that in this, there's an N. Now what's that 8? There's an ite. I mentioned a lot an ite. And an 8. All that means is every element has, every one of these polyatomics, the majority of these polyatomics rather, have the ability to have multiple different quantities of oxygen attached. So as an example, nitrite is N. Here, we'll do this, right? Nitrite, NO2. Nitrate, NO3. Again, a lot of the stuff is just memorization. If instead we were working with sulfate, I do want to double check myself before I give wrong information. It's SO3, SO4. And potassium is the exact same way. These are the 2 suffixes you're going to want to know if you're working with polyatomics. There are 2 prefixes. There it is. Per and hypo. This just means +1. It really just means referring to oxygen. The 8 one will always have more, and a per is just +1. Hypo is the ice, minus 1. So, taking what we know here, right? Nitrate, N. It's the 8, so it's the more of iterate, so it's going to be O3. This is nitrite, this pernitrite, and this is, that's hyponitrite, pernitrate. Right, there's an extra oxygen or one fewer oxygens attached on the end. All of these have the same charge, -1. The amount of oxygens does not change the charge, the overall charge. It will still be -1. Knowing this then, and it is, like I said, a lot of memorization, sulfur and potassium. The ones you're mainly going to be working with: nitrate, sulfate, phosphate, or nitrite, sulfite, phosphite. And they all have a varying degree of charge. Nitrogen is all -1. So here, we'll write it. And this isn't true, right? Nitrogen's -3, sulfur's -2, potassium is -3 as well. But in polyatomics, N is always -1. Sulfur, -2. Potassium, -3. Potassium nitrate then would be K. And the parentheses are used here as well. NO3. If this A were instead an I, that 3 would become a 2. Why is this in parentheses? The reason it's in parentheses is so that if you need a subscript, a 2 here, it doesn't mean that you have two O2s. What if you didn't have these parentheses and you instead just said NO22? People have no idea what you're talking about. These parentheses around it mean that of this group, you have 2 of them. On monoatomics, like potassium or sodium, or if it's a sulfate with a -2 charge, it could be magnesium with a +2. If it's a phosphate with a -3 charge, it would be aluminum with a +3. If there's only one of them, you don't need the parentheses, but if it helps you understand it easier, by all means, write the parentheses. Okay. Now is ionic bonds. In a nutshell, a 15-minute nutshell. But that is ionics. I should have went over this at the start. There's 3 kinds of bonds, but there's 2 kinds of bonds in chemistry. There's an ionic bond and a covalent bond. Ionic, intermission here. Ionic and covalent. Ionic just means that the cation ion and the anion, the positive and the negative, not pull each other apart, but that the anion pulls the electron off the cation, right? So take that Cl. No, that's the positive, no, that's the negative. In this relationship, the sodium has the atomic number of 11. It's 11 protons and it has 11 electrons to make up for the protons. Chlorine is 17. It has 17 electrons to make up for 17 protons. Every element wants a complete outer shell. That's the ultimate, right? Valence electrons are the elements that lay in, the electrons that lay in the outermost shell. Chemistry is just valence electrons. That's all it really is. And ionic bonds are the transfer of these valence electrons. Every element wants a full outer shell. And that's covered on earlier in the book. And now that I think about it, I should have started earlier than 2.8. I just want to teach stoichiometry. We'll get to that. We'll get to that. So think of it. Na. 11 electrons. And that's not at all what it looks like. There's different orbitals. And kick that can down the road. I'll teach that later. It's not necessary to know the orbitals and stuff for most chemical purpose. Like for a lot of the stuff we'll be doing, you don't need to know the inner orbitals and the outer orbitals. The orbitals themselves don't matter. It's just the amount of valence electrons. The general rule of thumb is that the innermost can only hold 2. And then every shell after that can hold 8. So 1, 2, 3, 4, 5, 6, 7, 8. That's one shell, right? This is shell number 1, shell number 2, and there's just a lonesome electron. Electron number 11. Chlorine, meanwhile, has 17 electrons. Shell 1, let me grab the thin marker for this. Shell 1, shell 2, and an almost complete shell 3. There's things another electron in here. So in sodium chloride, chlorine will take this electron, pull it towards itself. So there's another one here. And they'll have a full outer shell. And now with this one gone, there's a full outer shell here, and a full outer shell there. Ionic is when the anion pulls the excess electrons from the cation. So that's ionic. What's a covalent? Covalent is the sharing of electrons. So think, let's take a common molecule. We're going to take methane. CH4. 1 carbon, 4 hydrogens. If we were to draw it out, it kind of looks like this. And a lot of this is in the earlier chapters that I did not cover. It's preliminary knowledge. You should know this if you're learning chemistry. What do those lines mean? But I guess I'll review here. Why not? Single bonds. 2 lines, double bond, 3 lines, triple bond. There'll never be more than a triple bond. Each one, carbon needs 4 electrons to make up the outer shell. Hydrogen only needs 1. Hydrogen partially gives up 1 electron. Carbon partially gives up 1 electron. There's 2 electrons here. Hydrogen partially has 2 electrons. Outer shell is full. Carbon gets an extra electron. You do that 4 times, and look. 1, 2, 3, 4, 5, 6, 7, 8. There's the 8 electrons the carbon needs to make itself known. Now, what does this have to do with naming? I have to establish this first. Covalent molecules can really be almost up to the heart's content as long as it's realistic. So, remember that polyatomic? The polyatomic nitrate as an example, right? NO3. There could be pernitrate, nitrite, hyponitrate, right? Or we can go really crazy with it, N2O7. If we were to follow the Ionics naming structure, all of these would be nitrogen oxide. And that doesn't really work. And of course you can't just put on Roman numerals because -3, -3, -3, -3, it's all the same. This is where the use of prefixes. Can you guys even see all this stuff? Yeah, you guys can see this stuff. This is where a lot of I can't think of the word right now. Prefixes. You'll see a lot of prefixes. They go everywhere from mono to di, tri, it's quad and quint. Oh, nope. Tetra. That's just the first time. There's dodeca, domino, I think. It'd be 11, but we'll stick with these for now. And all this means that there's one of element name. 2, 3. Right. So instead of being nitrogen oxide, nitrogen oxide, nitrogen oxide, nitrogen oxide, this is instead nitrogen. This one would be trioxide, tetra oxide, dioxide. With things like mono or octo, if the element name starts with a vowel, especially with oxygen, you'll see it. You don't have to put two O's. It's not monoxide, it's just monoxide. Carbon monoxide is a well-known one. So what would this one be? This one would be, well, there's 2 nitrogens, 7 oxygens. So this would be nitrogen trioxide, tetraoxide, dioxide, monoxide. This one, dinitrogen septoxide. Just a lot of numbers. And I got that. So going back to that methane example, right? CH4. Methane is just its common name. It could also be carbon. Tetra hydride. And yes, you do use the ide from monoatomics. So methane could also be known as carbon tetrahydroxide, although that may look like hydrio-y with poor handwriting. So with all of that, I don't really have practice on you. This is really just stuff you have to work on memorizing. But you can't get very far if you don't understand what I mean when I refer to sodium chloride, potassium nitride, dihydrogen monoxide, right? So sodium chloride, it's 2 monoatomics, sodium chloride. And yes, there is supposed to be 1 T in potassium. I don't know why I put 2. Instead of repeating, right, potassium. And I'm going to put the parentheses here, but if it's just 1, you wouldn't really need them. Nitride, dihydrogen monoxide, dihydrogen monooxide. Wait, that's just water. You're going to learn that a lot of things have a lot of chemical names. Water, as an example, H2O, you can write it as H2O, chemical name, right? It's chemical formula. Water, we have it here, dihydrogen monoxide, could also be referred to as, in that atomic formula, hydrogen, and that's supposed to be hydrogen, I have poor handwriting, hydrogen, and then the OH negative, which is It's a hydroxyl. I believe that's how it's spelled. Hydrogen hydroxyl. Weird way of writing it. But all of these are all water. It's all the same thing. So that's a breakdown of the naming scheme. This is a half an hour long video, but I did get to explain a lot more than I wanted. I got to explain everything I wanted to in a decent amount of time. When we are back, we will talk about acids and bases. But that's the first episode. It's 2.8 from the textbook. It's all namings. We learned how to name monoatomics, name polyatomics, and name covalent molecules. Have a good day, have a good night, have a good evening, have a good afternoon. Whatever it may be.